Hello, in this video I'm going to look at exponential um, growth, looking at their graphs and their definitions. So with exponential functions, basically the idea is that the graph of them would look not exactly like a regular line or like a polynomial, but that it would have some kind of resemblance to this graph right here, where we have that it increases as x increases in terms of the that is. So we see that this one has a domain from minus infinity to infinity, but looking at the graph of this, it looks like it goes from 0 to infinity. Now, let's say that we wanted to look at a particular function that we define. And for the most part, a exponential growth function, it will look something like this, where you have f of x is equal to, let's say that you have some base and you raise it to the power x. Now usually, the thing that you would have to use is that this a, it's going to be somewhere between 0. Well, I think actually what we could probably do is just restrict a from being 0, and maybe also we'll strictly define a to be greater than 1. So this way we have that we won't have the 0 function, and we won't have any negatives, for example. I feel like maybe just positive. Yeah, that'll work. So we could probably just make it positive instead. Okay, because, what if you have like a half? That'll work, actually. So we have this function right here, and usually the key point that it passes through is, for example, like 0, 1. And you can kind of see that, like if you plug in 0 into that function, you have a to the 0, and what would that be? That would be 1. So we know that it passes through 0, 1 in either case. So this one right here, this point right here, that's actually 0, 1. Now, in either case, if we were to define this one specifically, so like if we said f of x equals to, let's say, 2 to the power x, well, we can see that basically if you were to plug in f of 3, what would that be? That would be 2 to the third, which is actually 8. So we have here that it would pass through the point 3, 8. And similarly, like if we were to look at, like let's say for example, f of -1, that would be 2 to the -1, which is actually just equal to a half. Now, of course, if you were to get any more points, such as f to the -2, that would be 2 to the -2, which is equal to 0.25. And we can kind of see that as x becomes negative but bigger, in any case, the values of f of x, they just get smaller. So either way, like if you were going to try to graph this, then it would probably be a good idea, to start with some points such as like -1, such as 0, 1, and then maybe 2, because in this case we already got 3, right? So here we got 0.25, we got 1, we got 2, and then we got 2 squared. Well, we didn't do that one, but 2 squared is actually just 4. So we have 4 for that one. Now, plotting these points, you'll see that this is actually the graph of f of x equals to 2 to the x. And, if we wanted to, we could plot these points. Why not? So here, this point right here, this one should be 2, 4 for this one. So that's 2, 4. No. Yes, 2 comma 4. And then this one right here is 1 comma 2. Okay. So here we have this graph right here, and of course, we can say that the domain of this is from minus infinity to infinity. Let's change that. Okay, so we have minus infinity, and then we have the range. Well, the range is from 0 to infinity. So we can do this for any graph as long as the a is always positive. And let's go ahead and actually define our function a little more specifically, because if we can identify the shape of the graph always, then in either case we can always have any other graph, whether it's 3 to the x or even something like negative 3 to the x, for example. So let's say that we considered our function f of x, and it was a to the x. And again, we're going to say that a just cannot be 0, and that a will be greater than 0. And in either case, like if we come back to how we had our graph of our function, so here we'll just draw a x-axis and a y-axis, and we'll go ahead and just draw the graph of an exponential function that goes something like this. And what I'm going to do here, though, is I'm going to note some important points. So one of the first ones is 0, 1. The second one is at 1, a. 1, a is pretty much when we take a and we raise it to the first power and we get a. But then the other point that I'll have is negative 1. So this one will be this point, negative 1, comma, and it's going to be 1 over a. So these are kind of like the key points in either case. And we can see that if we wanted to summarize the function, we can see that basically that analyzing, the graph of f of x, we can see that the domain is from minus infinity to infinity, and that the range is from 0 to infinity. Okay. Now, note that in either case that there are no vertical asymptotes, but you do have that there is actually a horizontal asymptote. So we have a horizontal asymptote at y equals to 0. Okay. Now, let's say that, for example, that we change our graphs just slightly, where we say, for example, well, what if we had this function g of x, and g of x is 2 to the negative x? Well, we know that, for example, that this is where the graph of f of x has that the base of it is 2. But here the difference is that you have that there's a negative x there. And essentially, if we were to look at this, for example, where we take that you have g of negative 1, that's 2 to the negative 1, but notice that that's going to be another negative 1, because you're plugging in negative 1, which is just 2 to the 1, which is just 2. So that means negative 1 comma 2. But similarly, if you were to plug in, let's say like 0, well, you get 2 to the 0, which is just 1. So then that means that it still passes through the same key point. But if we have g of 1, that's 2 to the negative 1, which is just a half. Now, if you're thinking, well, these are the same key points, but they're just in the opposite order. We have that, for example, this point over here, it appears that it kind of got moved over to the left-hand side, and then we have that the key point still stayed, right? And at this point, it's the same thing. It's like it moved over to the other side, which is also true. So that means that we can basically start plotting points, or if we were to use, say, for example, our graphing calculator, we could do that too, where we go to y equals, and let's go ahead and clear that out, and let's write in 2 to the, okay, so we're going to use minus sign, we'll put an x, and then for this one, we'll just go to zoom standard. And see like how we have the graph of f of x is now, it's actually now decreasing on its domain. So we could, draw like a rough sketch, even though like we already sort of saw it using the graphing calculator. If we were to plot those same key points, we would just tell ourselves that the graph of the function, it's still sort of the same shape, but this negative sign, what it did to the graph of its original is that it reflected it over the y-axis. So in that case, that means that we have that the graph would look something like this. And, what we'll do is we'll just say, well, what are the key points? We have 0, 0, 1. So that's 0, 1. And then, if you want to just put to scale that this is 1, then in that case, this will be 1, comma, the half. And then over here at negative 1, this will be sort of like the key point, 1, comma a, but it's reflected actually. So in this case, we have that this would be minus 1, comma 2. So here we have our graph of f of x, or in this case, we're saying g of x. Okay, so here is our graph of g of x, and we can see that it still has the same shape. It's, in this case, it's decreasing as we go on its domain. Of which, if we wanted to specify things about the domain, we could say, well, did the domain change? It did not, based on the graph. We have that it still goes from infinity, negative infinity to infinity, and then the range, well, the range of this did not change either. It still is from 0 to infinity. So we would say that we do have a horizontal asymptote, and that horizontal asymptote will be at y equals to 0. So if we were to just put, we have a horizontal asymptote, we would just put that it's at y equals to 0. Now, if we were going to, let's say, for example, change the graph of this function, like if we were to say, well, I'd rather just look at, let's say, like 3 to the x, you'll see that nothing really does change, actually, in terms of the shape of the graph because of the way that we defined our original exponential function as a to the x. So, if we have, for example, a function and we call it h of x equals 3 to the power x, the key is that nothing would change with respect to the domain and the range, but that you would still have that it passes through those key points as mentioned, how if you plug in negative 1, that's going to be 3 to the negative 1, which is actually 1/3. and then you have 0, comma 1, which is the key point 3 to the 0, which is just 1. And then you have 3 to the 1. I think we have this backwards, but 1, comma 3. So you would be plotting basically these points in either case. Now, if, for example, that you wanted to see further, points, you could do that too. Nothing wrong with that, right? Where if you plug in 2, what would you get? Well, that would be 3 squared, which is actually just 9, so you get 2 to the 9th. And then you see that if you plug in 3, well, that's 3 cubed, which is 27. So basically, you're just plotting these points in either case. Similarly, if you plug in -2, that's 3 to the -2, which is 1 over 9. But in either case, you would see that, does really anything change with respect to the graph? And the answer is actually no. Is that you have that, the only difference is the factor of which that it's increasing by, which in this case, it's increasing by a factor of 3. So normally what I would do is I would just, once I've verified that the graph of it would not change, that is the shape of it, then in that case, I would just go ahead and plot or draw the exponential graph, and I would use that it passes through 0, comma 1, and then from there, we'll just pick that this would be 1, comma 3, and then over here we would have that this would be -1, and then 1 over 3, for example. And what you would see is that even if you analyze the domain of this one, you have that it's still from -infinity to infinity, and the range is from 0 to infinity. So here we have the same graph, essentially. And, if you wanted to, you could go back and change this graph to, let's say, like 3. Well, let me just clear that out, right? So 3 to the power of x, and we go to graph, and you see we have more or less the same graph. Okay. Now consider this, though. Now, in the event that you had, for example, this function, let's say like you had y is equal to -2 to the power x, and then you have that it would be +2. Well, the thing about this is that you would have to identify what are the transformations. And the transformations would be that you have 2 of them, actually. You have that you're going to go up by 2 units, but what is this negative sign doing? It's reflecting the graph over the x-axis. So what that means is that the horizontal asymptote would be at y equals to 2, but the graph of the function would actually just be reflected in this case. So it's almost like saying that if you had the ordered pair 0, 1, it would pass through 0, 3, but you have to reflect it now over the x-axis in this case. So I think that in order to do that, though, we're going to see that it passes through actually a different point, actually. So let's look at this. Okay, so we have that it's definitely a reflection over the x-axis, right? So if we were going to plug in 0, yeah, it would be 3, but we have a negative sign here. So that means that it's actually going to be shorter. And it's going to be shorter by actually 2 units. Yes, because the horizontal asymptote, it would be y equals 2, right? So when I plug in 1, I expect that it was going to be 3, so it's up by 1 unit. Hopefully that makes sense. That it's up by 1 unit. But then, because it's reflected, it's actually the opposite. Okay, so that means that, so what I'm trying to say, I guess, is that if you plug in 0, so here you have y equals to -2 to the 0 plus 2, but that's equal to 1. So here you have that when you plug in 0, that it's going to be equal to 1. Now, if we go ahead and we look at this also, if we plug in y to the 1, or sorry, x is equal to 1, so this will be -2 to the 1 plus 2. This is actually going to give you 0. So we have that it passes through 0, 0. Now, if we were going to, let's say, for example, let's see, we've raised it to the 1 already. If we go ahead and we, say, for example, plugged in -1, well, that's going to be -2 to the -1 plus 2, which in either case, that's going to be 1.5. So we have 1.5. So you'll see that as you make these values even smaller, that this part, the -2 to the x, is going to get smaller, which means that in either case that it's never going to reach 2. Okay. So we have -1 and 1.5. So think of it this way, and we'll draw the graph over here. If we draw the graph over here where we say that, for example, we've identified that there was a horizontal asymptote at y equals to 2. And the thing about this is that it's saying that it's passing, I'm not sure, let me see. When I plugged in 0, there's something not right. This should be 1, 0. Okay. Yeah. So this point over here, the one where we plugged in 1 for x, that should be 1, 0. Okay. So so in this case, we have that, yeah, so we're going to plot these points. We have 0, 1, we have 1, 0, and we'll try to get the sketch as best as possible, but we'll just draw it like in a way that, let's see, it comes from this side, and actually, that's not going to work, right? So let's do this. Okay, so here I am giving a rough sketch where it passes through 0, 1, and it passes through 1, 0. And then, of course, you can plot -1, 1.5. So maybe like, maybe that'll be right about here. So that'll be -1, 1.5. Now, this one right here, this is y equals to 2. That's the horizontal asymptote, as we can see. And if we were going to analyze the domain of this function, well, if we're going to analyze the domain of this function, you would see that the domain of this is all real numbers still. So not much changed, but the range has changed, and it's from 0 to infinity. So here we have that that's from, sorry, that's not correct. Actually, that should be from -infinity to 2. Okay, so here that's going to be from -infinity to 2 for the range. And of course, if we were going to plug that into our graphing calculator, that would give us more or less the same thing. Now, this next part, it requires basically using the scientific calculator. So there is a special function that we define, and um, that's the e function or the exponential function. And I know that we're talking about exponential functions, but specifically it's for this graph where we have f of x equals to e to the power x. Now e is a number that is approximately 2.71, and then it just repeats. So, like, to get an idea of like what is that? Well, take a look at if we were to use second e, and then we go to 1, and we hit enter. That's 2.71828 and some change, right? So this is a number that is used a lot in science, in business, in applications that involve like continuous growth, for example. And if we were to look at this function, we could probably say, well, what if we looked at the graph of it? Because see like how the constant e, it's less than 3, but it's less than, or greater than, it's greater than 2. So we know that it's somewhere between 2 and 3. But either way, it's not very common that, you would just use like an estimate, for example, like 2.5 or something like that. Or even just say, well, my graph is 2.72 and it's raised to the x. It's normally accepted that you just write e to the x. So if, for example, that we were to draw its graph, and this graph, it would not really change much because you have that e to the 0, well, that's just 1, so we know that it passes through 0, 1. But then, e to the 1, well, that's the one where we found that it's 2.71828 and some change, right? So you could just say, well, that's just 1 to the e. But if you use e to the negative 1, well, that's going to be 1 over e. Now, granted that that's somewhere between 2 and 3 for the e, well, 1 over e, we could probably just do this, where I'll just do 1 divided by the previous result. And it's like 0.37. So my rule of thumb is that, if that's a 3, then it should be a little bigger. So that should be close to a third, right? So you can see that as the x gets bigger, that it gets smaller. So then that means that the graph of the function, if we just draw it here, it's still going to have more or less that same shape, where you have that the graph of it increases on its domain, and then you have that it passes through those key points. Those key points are, of which that we mentioned, -1, 1 over e, and then you have 0, 1, and then of course you have that it passes through 1, e. Now, for the purposes of this course, this function is specifically designed to look at exponential growth that is continuous when it comes to an amount of which that you, let's say, like deposit. So let's say, for example, that we model this in a way that we have that the function, it can be redefined in the following way, where we have y equals to, let's say, like, for example, that you have some initial amount, we call it p, and this is times e to the rt. Now in class, you've already learned, like, when you have a principal amount, so p equals the principal or the present And then you have R is the interest rate. And then you have T. What is T? Well, T is just time, actually. So this means that we could look at any application of that is dealing with exponential growth. Now, of course, if R was negative, then we would be talking about the opposite. You'd be talking about exponential decay. So let's say, for example, that you have deposited $100. And the annual interest rate for this one would be, let's say, like 0.06%. Or, yeah, 0.06, which is 6%. So let's say that this money, it's going to sit around for, let's say, like just 2 years, for example. Okay, well, if we want to find the value of this amount, that means that we would set it up like where we have y equals to 100 e to the 0.06, but it's multiplied by 2. So for this one, we have to basically just use the stored value of e, and that's going to be 0.06, but multiplied by 2. And we'll see that basically that this amount is 112.75. So here we have that this amount, it is 112.75. So here we have that this is an amount of which that it grows exponentially, and the value of it, it's very interesting actually, because if we were to compare, for example, an amount that it wasn't really continuous growth, but let's say that it was, given by some kind of period, like whether it's monthly, annually, semi-annual, and so on, like what we could do to compare, for example. So see like how the interest that it grew was $12.75 in just 2 years. Well, what if we compared that to if we take an amount that's the principal, and that's 1 plus an interest rate divided by a compounding period raised to the number of total periods. So let's say that we compared where we had that the principal was 100, the R is equal to 0.06, and the T is going to be for 2 years. But let's say that we take that the maximum, or the period for this one, let's say that this one was for 12 months, the compound period, so monthly. Well, in this case, we have that would be y equals to 100 multiplied by 1 plus 0.06 divided by 12, but raised to, well, here, notice that that's going to be raised to the 24th. So we'll put to the 24th. Now, technically, we can put 12 times 2, and then, yeah, sure, that's 24. Now, I hope that you realize that this number inside the parentheses, this is sort of like the value of a in this case, and then you have an exponent to the 24. So here, let's see. So we know that, let's say that we look at the interest, so 0.06, and this is divided by 12. So that's 1.005. Okay, so the only reason that I'll do that is so that you can see that this is 1.05, and that's raised to the 24. So see like how we have an exponential expression in this case, I think it's 0.005, right? 1.005, and it's raised to the 24, but it's multiplied by 100. So here, let's see what that gives us. So, yeah, we have to raise that number by 24. So that's the amount of which that it grew in terms of the factor. Okay, so What are we going to do with that? We're going to multiply by 100, right? So basically I kind of did it separately. And see like how this has that it came out to 112 and 72 cents. So that is 112 and 72 cents. So in comparison, we have that there is a 3-cent comparison in this case where we have that the interest was greater for whenever the amount was continuously growing, but then you have that it was less for when it was compounded on a monthly basis. So more or less what we're saying is that the interest will never exceed 1275 within the given 2 years. So that means that hypothetically we would know the maximum return rate of interest or earned interest within a given time frame, because notice that if you were to look at, for example, the amount of which that you have 100, and let's say it's multiplied by the factor of 1.005, but that's raised to, let's say that, okay, well, instead of 2 years, let's say 5 years. So that would be 12 because it's monthly, but times 5. And then let's see what that gives you. It gives us 134.89. Okay, so $34.89. But let's say that, for example, that you calculated continuous growth. Well, in this case, you have that would be the interest rate, so 0.06. But how long is this for? For 5 years. So see how there's a 10-cent difference because you have that this would be 89 and this would be 99. So that means that the interest will never exceed 34.99 in this case. So even if we were to, let's say, for example, use that the growth for the cash was compounded on, let's say, like a daily basis, you would have that amount will not exceed essentially what we found here. It will not exceed 134.99 cents. And just to show you real quick, like if we have 1 plus 0.06 and we divide by, let's say, like 365. So this is the amount of which that, that it's going to grow by. But here we're going to raise it to 365. And let's say that that's for 5 years, for example. So this is the amount of which that it's going to grow. And we multiply that by 100. And see, we have that's going to be 134.98, which is off by 1 cent. So in this case, even doing a situation of where we have a daily compounds, it didn't really exceed, or it actually didn't exceed the 134.99. So in this case, like we see that the value that we got for the exponential case, it's more or less like a sort of like a guide and letting us know like how much the interest will never reach, or like what's that limit, if that makes sense. So here we have that the value of it was kind of like restricted in either case. And you see this function a lot in things like inflation rates in economics or business. I actually know it more from a science perspective where we look at exponential growth and decay because, for example, if I knew a certain population and I knew the rate of which that we talk about like birth rates, for example, then in that case I can look at population growth. But that's unbounded because, like if you look at the graph of this, it's actually unbounded too. But in any case, like if you're looking at it from 0 to 10 years, then it's not unbounded. It's actually, restricted, right? So I know it more from a science perspective of where it talks about like growth or like decay of a, bacteria or things like that. So either way though, for us, I think that we're more interested in like, for example, at least population growth, for example, or even, the finance side of the exponential function where we're looking at it in terms of, the growth of something. And, that's kind of like the whole basis of, when we talk about finance with regards to like, double time, triple time, etc. Like if we wanted to look at the value of the dollar, how $1 could go from being worth a dollar to, let's say, being worth twice its amount, for example. And we could find that, for example, like if you had that, you look at, if you have $1 and that's times E and that's raised to, let's say, like, for example, like 5 years, and then you have that that's equal to twice its value. So that would be equal to, let's say, like 2. And the key to this would be, well, now I have e to the 5r, and that equals to 2. And the question is, well, how do I solve this, for example? And the solution actually would be that we would have to essentially look at this exponential graph. So, for example, we know what the exponential graph would look like, right? We know that it would be something like this, but then what is the 2? It's a horizontal line. So here we're just looking for where those two would intersect. So we could probably do that where we just have y equals to, let's say, like e, and that's to the 5x. Maybe just clear this out. Okay, so second, e to the 5x, and then this is a 2, and then we go to graph. So here I just need to look for where they intersect. Now, what I'm doing here is I'm utilizing the technology in order to find where the two intersect. And in either case, we're going to learn more as to like how do you do that by hand if we are not going to use a calculator. So see like how here it's telling me that the interest is at 13.9%. So that means that if we wanted a dollar to be twice its value, then in 5 years we have to have that the interest would be at 13.9%. Okay, so we have that here, that R is approximately 13.9%. And, you could probably do the exact same thing for which that, let's imagine for a moment that if you went and you had $1,000, and let's say that the interest rate of it was at 5.5%, and this was compounded on a monthly basis, and if you wanted to find when the time of it would be such that the accumulated amount was 2,000, we'll see like how that's more or less like a exponential problem where you have that's going to be 2,000 equals to 1,000, and that's going to be 1 plus 0.055 divided by 12, and this is all raised to basically 12t. And see like how now this becomes an equation that you could probably solve, where you have that either you're isolating this or you're just, finding where these two would overlap, for example. And, just to give you an idea of like what is that, that is 1 plus 0.055. This is divided by 12. This gives you only just the factor of which that it grows by. So this is the factor of which it grows by, which I would not recommend rounding it. But here, this is basically the value of which that it grows by. So we could determine like where the time of it would double. And for now, we'll have to solve this equation using a calculator. That voice that you might have heard just now, that's my oldest. So here, like, if we were to solve it, we would have to use basically like using what is called a logarithm. So this, for now, you can only solve using, where you set the two graphs together and you use the intersection of them to get what the time of it would be. Now, if you do that, then that would be, so sure, why not? Let's go ahead and solve it. So clear 2000, and then we have 1000, and then that's going to be 1 plus 0.055 divided by 12, and this is raised to the 12t, but here we're using x, right? Okay, so let's say that we graph this, and now note that the interest rate has to be, or the time actually, right? Time. Yeah. So here, let's see. Let's change the window where we use that x is from 0. And I'm not really sure as to like how long it's going to take, but let's say 20. Let's go up to 20. And the scale for this one, well, it has to be 0. And for the maximum, well, we're trying to look at when it crosses 2000. So we're just looking for the doubling time, basically. And we'll just use 2500 as the max, for example. So here we'll go to graph. Okay, so here we have an exponential graph, and we have the amount that it reaches, right? So second, trace, and we'll use the intersection. Okay, so it is going to take approximately 13 years for this amount to double. So, yeah, so this is 13 years, nearly, for the amount. Because after, if you look at it like this, like, after 13 years for sure, it would have doubled. So, I mean, if you want to say 12.6 years, you can. So, the time for this one is approximately 13 years. So after 13 years, the amount will double. And that's due to the fact that, it's compounded on a monthly basis. And truth be told, I don't think that there would be any situation of which that, you could probably say, well, what if we had that it was continuously compounded and you had that it was e to the 0.055 t, and that's equal to 2000. Now, in this case, like if you've ever taken like a science course of which looks at doubling time, you could probably just say, well, why don't you just use that it's ln of 2 and then divide that by the rate of which that it grows, which is 0.055. And see like how it is very close, actually. It is very close in that it's telling you that it's in uh, basically 13 years also. But the difference is that it's not growing at the same rate. So for the one that we had over here, it was growing at a rate of which that it was monthly. But in this case, you know, if you do it like this, like where it's growing continuously, then it's not monthly anymore. It's like every single moment that is available from 0 to 13 years. So in this case, like we will look at some more applications of exponential growth and how we can use them in certain situations, like you know, finance, science, looking at the growth of a population or looking at the decay of some type of sample. And this is used a lot, like in even things like geology. Um, so yeah, we'll be looking a lot more at this topic, but we'll be also looking at, you know, situations of which that would not necessarily be exponential, but they would be also logarithmic. So hopefully like this helps in terms of like, you know, getting down to the basics of, you know, what is an exponential function and how they can be used.